This presentation is given by myself, Joe Hayes, the inventor and CTO of Vistigo Limited. The evolution of sound. Let's look at this first. 1877, Thomas Edison is the first to successfully record sound. He recorded Mary Had a Little Lamb on a tinfoil cylinder phonograph. 1921, Kellogg and Rice invent the moving coil loudspeaker. All of these here are examples of loudspeakers derived from Rice and Kellogg. 1935, the German company BASF first demonstrate magnetic tape publicly. 1948, introduction of the vinyl LP developed at Columbia Records. 1965, Dolby A-type noise reduction is introduced. 1982, the first digital CDs are marketed. 2015, ICOM reinvent the moving coil loudspeaker and name it Rotorsonic. It is only the Rice and Kellogg innovation, circa 1921, that was specifically for the loudspeaker. Loudspeakers have remained principally the same up until 2015, when I developed the acoustically integrated Rotorsonic solution. What we do that others can't. Conventional loudspeakers, all speakers that have been used since Rice and Kellogg invented the moving coil loudspeaker in 1921, and Rotorsonic speakers, the audio technology invented by myself that finally solves the inherent problems with moving coil loudspeakers. Conventional audio is not immersive and experiences the adverse effects of reflections and reverberations from any object in the listening environment. With Rotorsonic technology, the audio sweet spot is achieved in all parts of the listening space, avoiding the need for surround sound or any other technology that tries to imitate an immersive audio experience. Rotorsonic prevents reflections, echoes, reverberations, and reduces noise, creating an immersive field of sound. Our technology represents an evolution in the moving coil loudspeaker. Conventional speakers simply can't do what we do. This is what our sound looks like. We call this dark side of the room. The direct energy will travel to a reflective surface, but then the reflection angle is dependent upon the frequency. So what we've done, it means that we call this diffusion at source. The sound will go past the listener, and as soon as it is reflected, it becomes dispersed. It takes the specularity out of that sound, and it no longer becomes part of the psychology of the listener. How others appear using the same model, light side of the room. So when the direct energy hits a reflective surface, it reflects, all frequencies reflect at the same angle, which means that the coherency is maintained, and we hear this as an echo. We hear this as a subliminally conscious echo. Our competitors do not deal with the listening space acoustics. Alternatively, they use headphones to both block out the listening room acoustics, but at the cost of surrounding the live portion of sound enjoyment. The problem with lighting up the listening room, meaning audible reflected echoes, is that these audible echoes reduce clarity and intelligibility. Clarity and intelligibility, once heard from a loudspeaker, is a strong emotional event that converts people away from their prior experience of what a loudspeaker sounds like. So why are we so far ahead? 30 years developing the technology to the point we have the technical superiority over others. This includes 2 mathematical models, one in MATLAB, the other in COMSOL. With COMSOL, we can model almost any application. We have 3 different ways to build a Rotorsonic solution: the reflector, the passive manifold, and the digital array. Let's look at the reflector. Is first generation, high tolerance, difficult to control in manufacturing, which led to the passive manifold and the digital array. If we're looking at by market, miniaturization, which might be smartphones, in auto, cars, TV or sound bars, this is really driven by real estate issues, particularly in smartphones. The size of a smartphone is limited, therefore a fierce competition exists for room within the final product. Our solution is a Rotorsonic algorithm driving a small MEMS driver array. With something released by USound recently, we could get this to 7mm by 40mm by 3mm. That's the sort of size that the smartphone people will accept. The disadvantage is a bill of materials increase because you have 7 drives instead of 1. but given the advantage of sound superiority, that ought to be absorbable. The medium-sized solution, this is mid-fi, hi-fi, consumer audio, small PA, public announcement, does in ceiling speakers, automobiles, TVs and soundbars. This is driven more by the dollar's bill of material. Our solution is a manifold made in ABS or the like. It's injected molded passive arrays. The advantage is an ease of inclusion to existing design methodologies, minimum BOM impact for dollars. Disadvantage is a mechanical solution only, so counterfeitable if that was out there. The advantage of an algorithm and chip is a little bit more discretion in hiding the technology. This is the passive array here, and on the outside of a box it looks like 7 slots. Continuing this third area of application is if you want to do a massive size, concert PA, big cinemas, was driven by power handling. Our solution is the Rotorsonic algorithm driving powerful driver arrays. It's pretty easy to include in existing design methodologies. It helps manage its feedback. The disadvantage is the concert experience will be so different, it evokes a paradigm shift in what a concert experience is. We think it's highly favourable, but where you get ultra clear clarity and no feedback, that's something new for concert PA. So spatial envelopes explained. Let's get a little deeper technically into how this works. A conventional loudspeaker has a circular spatial envelope. Like a pebble dropped into a pond, the energy flows out in all directions as a circle. Fair enough. A conventional speaker has this circle spatial envelope. It's like where the ridge of the energy is. If we look at a Rotorsonic spatial envelope, the Rotorsonic speaker has an elliptical spatial envelope. The energy flows out in all directions like a circle, but the peak ridge follows an egg shape. And the egg shape is frequency are locked together. So you change the frequency, you change the egg shape. Take a conventional audio, pretend there is a wall of sound on either side coming from the speaker. Because it has all frequencies have the same spatial envelope, the wall of sound doesn't move as the frequency changes. This is how the wall of sound behaves under Rotorsonic audio. We have 5 bass notes coming through, each with a different frequency. Therefore, even though it's an omnidirectional sound, the position of the peak ridge within the sound field will move with frequency. So when we play a complex piece of audio through, the wall of sound is literally moving with the pitch of the music. So we've just put back this whole new dimension that's lost through conventional speakers. So the Rotorsonic walls of sound are shifted by the frequencies playing through it. Thus, those human and environmental sub-50 Hz cues will cause the wall to move. What I mean by this is what changes the frequency in music is a musician. Now, humans can't do anything faster than 20 times a second. Even in acoustics, if we do something more than 20 times a second, it becomes a blur rather than individual notes. So we put back this movement that helps us perceive the presence of humans in the audio. Put it another way, the Rotorsonic wall of sound will move when a guitarist plays a different note or bends a string, when a singer inflects on a word, when the newsreader speaks or emphasises a word, and when recorded reverberations play through. These moving walls of sound cannot be echolocated within a listening space as they are constantly moving. So the listener is totally immersed in the audio without any consciousness of the acoustics of the environment in which they are listening. It is more difficult to establish a feedback loop on a shifting sound field, so this is a major pain point for live sound. So for an immersive audio experience, Rotorsonic sound technology.